Welcome back. Today we're exploring the fascinating world of acids and bases. These fundamental concepts are crucial, not just in chemistry, but in many biological processes as well. We'll be diving into the definitions of acids and bases according to both the Lewis and Brønsted-Lowry theories, understanding their strengths and discussing some common functional groups. Let's get started. In an acid-base reaction, an acid and a base react together to form a conjugate base and a conjugate acid. This reaction only proceeds if the reactants are stronger or more reactive than the products formed. Essentially, the reaction moves towards the formation of weaker acids and bases. For the MCAT, we focused on two main definitions, Brønsted-Lowry and Lewis. The Brønsted-Lowry definition is all about proton transfer. Here, an acid is a species that donates a proton, while a base is one that accepts a proton. Some molecules, like water, are amphoteric, meaning they can act as either an acid or a base depending on the environment. For instance, in an acidic solution, water can act as a base by accepting a proton to form H3O+. In a basic solution, water donates a proton, forming OH-. The Lewis definition takes a different approach by focusing on electron pairs. A Lewis acid is an electron pair acceptor, often seen as an electrophile with vacant p orbitals or a positively polarized atom. Lewis bases are electron pair donors, typically nucleophiles, with a lone pair of electrons that they can share. When a Lewis acid and base interact, they form a coordinate covalent bond, where both electrons in the bond originate from the Lewis base. This is crucial in many organic reactions and enzyme mechanisms. Now, let's talk about acid and base strength. The acid dissociation constant, Ka, measures how well an acid donates its protons in solution. For any acid HA dissociating into H+ and A, the Ka is given by the concentration of the products over the reactants. The pKa is simply the negative logarithm of Ka. The lower the pKa, the stronger the acid. Acids with the pKa below -2 are considered strong acids because they almost completely dissociate in water. On the other hand, weak acids have pKa values between -2 and 20. For example, carboxylic acids, which have a pKa around 4, are stronger acids compared to alcohols, which have a pKa around 16. Understanding these values helps predict the behavior of different molecules in a reaction. Functional groups behave differently as acids or bases. Alcohols, aldehydes, ketones, and carboxylic acids act as acids because they can donate protons. In contrast, amines and amides are basic due to their ability to accept protons or donate a pair of electrons to form coordinate covalent bonds. A special mention goes to alpha hydrogens in carbonyl compounds. These hydrogens are slightly acidic due to the resonance stabilization of the conjugate base, known as the enolate form. This property is important in various organic reactions, including enolate chemistry, which we'll cover in more detail in future videos. And there you have it, a comprehensive overview of acids and bases, their definitions, strengths, and behaviors in organic chemistry. Whether you're dealing with simple acid-base reactions or more complex mechanisms involving functional groups, understanding these concepts will help you tackle a variety of problems in chemistry and biochemistry. If you found this video helpful, don't forget to give it a thumbs up, share it with your friends, and subscribe for more in-depth chemistry content. And if you're using the King of the Curve app or web app, be sure to like and comment on what topics you'd like us to cover next. Check out the app for more detailed content, quizzes, and study tools to help you ace your exams. Thank you for watching, and good luck studying.